All right. Looks like we got a good crew on. You ready, Katerina?
Here, I'm ready.
Great, great. All right. Well, thanks so much to everyone for joining us today for our public webinar for the Concrete Sustainability Hub. I'm Jeremy Gregory, and the Executive Director of the Hub. And we do a variety of different topics within the Hub. And we're fortunate enough today to have a research presentation on some of the work that we've done related to durability. And Katerina Yanadu, one of the PIs in the Concrete Sustainability Hub with some other affiliations she'll talk to you about, is going to be sharing the work that was done. So just so you know, everyone by default is muted, but in the lower right-hand corner of your screen is a Q&A box. And so what I'd encourage you to do is if you have questions, please type them in there, and then when Katerina is done with her presentation, we'll use that as an opportunity to allow you to ask questions that she can then answer. So with that, take it away, Katerina.
Okay, thank you, Jeremy, very much for the introduction. I am Katerina Ioannidou. I'm a research scientist at the University of Montpellier and CNRS, and also at MIT in the joint lab between CNRS and MIT. And in the past, I've also worked for the Hub. So the work I'm going to present you is in collaboration with Tingtao Zhu, who is a PhD student at the Hub. So I'm going to talk to you about multiscale poromechanics of wet cement paste and its implications to durability. So we'll start with the basic things of cement production. So as you all know, cement is an irreplaceable material for construction, but it comes with a big environmental impact. So 5 to 8% of the anthropogenic CO2 is coming from the production of cement. And excuse me for a moment. And we also know that the cement consumption at the moment is really large. For example, in US, China consumed in the past 3 years the amount of cement that US consumed in the past 100 years, and this trend is only foreseen to increase as the population is growing, and also we have an intense urbanization. So basically here you see the prediction of United Nations of how many cities of the size of New York we are building, and also the projection of how many we are gonna build. So this trend is only foreseen to increase. So this means a huge amount of cement is gonna be poured in the coming years. And ideally, we want the material to be very durable. So the buildings we're building, they're standing there for many years. So unfortunately, there are a lot of problems with cement and concrete. So usually we have a nice slab of cement, and after a year or hopefully more than 1 year, we have the formation of many cracks and fractures. And two of the main problems that we have been studying a lot at the Hub is degradation due to freeze-thaw and due to alkali-silica reaction. So both of these problems have a common feature. We basically have a crystallization problem in a porous medium. So the porous medium is the cement paste and the concrete. And in both cases, we have a new phase forming in the porous network. For example, in the freeze-thaw, we have the water crystallizing. And in the case of the alkali-silica reaction, we have the formation of a gel due to the silica-rich aggregates that exist on concrete. So this is the common feature of these two durability issues, but they have a little bit of different conditions why this is happening. So in the case of freeze-thaw, the problem is the drop of temperature in the winter. And also this problem is getting worse as we are adding de-icing salts in the surface of pavements to prevent accidents. This is making the problem even worse. An important point is that in order to have this type of damage, we need to have a high degree of water saturation. So the material needs to be saturated with water, otherwise damage is not observed. In the case of alkali-silica reaction, the reason why we have this damage is the silica-rich aggregates that they start reacting after many years inside the concrete. So basically, the presence of alkali is the reason, but also in this case, we need the material needs to be saturated in water, otherwise the damage is not propagating so fast. So as you notice, we have here the two different reasons why we get this damage. And in each case, we get a different phase. So in the freeze thaw, we have ice. In the alkali-silica reaction, we have a gel phase. So it's a soft phase. And actually, it's a problem of solidification, as we can say better, instead of crystallization, because it's not a crystalline phase always. But what is very important in both cases is we need to be saturated with water. So basically, one of the key problems is where is the water how the water is distributed inside the pores of cement, and how is causing the damage. So here in this cartoon, you see the reason why we have damage. So here you see a pore of cement, and inside the blue is the new phase, so the new crystal or solid that is forming. And during this process, we have the confinement of the ions between a nanometric layer of the cement and the new phase that is forming. So basically, this confinement of ions is building up an ionic pressure, and this is what is pushing both solid phases. And if the new solid phase is as strong as cement, then the damage is start passing by also to the cement phase. So here the new thing is that not water only is important, but also the ions. So with these things in mind, I will try to show you how simulation can help us to gain scientific insight on durability issues of cement and concrete. And we will start first to see what are the relevant length scales to explore these questions. And then we'll try to understand which pore sizes matter for this type of problems. Does the connectivity of the pores play a role? And then, of course, the key question is, what is the role of water, the solvent, and what is the role of ions? So, as you all know, and we have been discussing this a lot through all the years of the CSH Hub, cement is a very multi-scale material, and it's very messy in many different scales. Here you see a diagram of the different scales of cement and concrete, starting from a few angstroms, where we have the chemistry of calcium silicate hydrates, the glue phase of cement, and going all the way up to the concrete, where we have the fine and coarser aggregates. So the past years we have done a lot of work to try to connect the atomistic scale that you see on the left with the mesoscale that is in a box in the middle. So basically we have tried to upscale properties from the atomistic scale, so basically the chemistry of calcium silicate hydrates, into a particle-based model through the interaction of these particles, and to understand how this is influencing the texture and the mechanics of cement. So in this work here, we went one step further, and we also introduced water and ions in the pores of cement to see what is the effect on the mechanics of this porous material. So I will start showing you here an X-ray tomography of a piece of cement. So here you see a piece of cement, we are scanning it through. So the white part is the unreacted clinker, the gray part is the cement paste, and the black is the porosity. So the resolution, the pixel resolution is 64 nanometers, and this was a slab of 35 and 60 micrometers. So the red network that you see here, this is the pore network of cement. So as you can see, it's very complex, it's very tortuous, and actually it's connected up to 95%. So basically, all the pores of cement, no matter what is the size, they are connected with each other. Very few pores are isolated in the material. So that's a very important feature we should keep in mind when we try to model all these type of durability issues. So here you see basically the view of this material from simulations at the smaller scale. So basically the simulation box that you see here is around 0.5 micron. The gray sphere is the calcium silicate hydrate. You see them on the zoom on the side, which are nanograins of few nanometers, around 5 to 10 nanometers. And these nanograins, if we zoom in inside them, they have a very complex atomistic structure that you see on the bottom. And in this type of scale that we are working here, the mesoscale, we don't keep all the chemistry, otherwise the simulation will be very heavy, but we carry this chemistry through the effective interactions of the calcium silicate or cement hydrates. And I've been explained many times in the past how we've done the simulations. So what are the effective interactions that they're arising from ion correlation forces, and then with the right simulation techniques, combining Monte Carlo and molecular dynamics simulations, we can have a structure which is very heterogeneous, and it gives a very interesting pore structure that it has basically the two main features that one sees in experiments for cement. These are the gel pores, the ones you see on the left on the zoom in, which are pores of 1 to 5 nanometers that one is finding in between the close pack cement hydrate grains. And then we have the capillary pores, which are pores between 5 and 50 or even larger 100 nanometers that one finds on the way that these grains are forming clusters and they are aggregating into larger structures. So what I've just shown you here is the cement grains in gray. And if we visualize the opposite, the pore space, you see it here in blue. This is a space that will be filled in with water, and it will be filled in with water in a different degree of saturation, depending the type of simulation we'll do. And also I want to show you the pore size distribution that we get from simulations, and we have validated from experiments that it has exactly the two features that we find on experiments, which is this first peak of gel pores, and then this very broad distribution on the capillary pore sizes. And now let's enter our main question, which is what is the role of water in cement-based poromechanics? The work I'm going to present you has been published recently in these two papers, and it's in collaboration with Tingtao Zhu, PhD student at the Hub, that he also graduated yesterday. Congratulations, Tingtao. And so let's go into our main subject. How is water distributed in the nanograins of cement? So here in this cartoon on the top view, you see what usually is people are trying to model. So they model water between grains as capillary bridges. So this is the pendular regime, where one can model this as a spring, or it's an easy way to calculate this type of water distribution. But as we increase the relative humidity, as you can see on the funicular and then on the capillary regime, there are no clear capillary bridges. Basically, the water is forming clusters that is joining all the grains. So we are interested to understand how the water is distributed around one grain, how the water is distributed in between many grains. You see the example of the 3 grains, but also in this very complex material that is called cement, that has a lot of tiny little pores that are all connected. So to do so, we start with the cement paste model that I showed you before with the grains, the one on the left. And we take this particle-based simulation and we turn it into a lattice. So we have a lattice that its point can be either a fluid or a solid. And what we did was density functional theory. This is a mean field approach where we write a thermodynamic potential that takes into account the interactions between the fluid-fluid and the solid-fluid. So what is important is to calibrate these two parts, the fluid-fluid and the solid-fluid, from the formations of the materials that we are modeling. So in this case, the fluids we try was water and nitrogen because that's the two common fluids where people are trying to probe the pore space of cement. And we also calibrated the solid-fluid interaction from atomistic simulations. And here a very important point is that we try to see how a piece of cement, which is around half a micron, is interacting basically with the fluid, the water, where water molecules are very small. They are 3 angstrom. So basically, we had to make a grid of this lattice that is as small as the water molecule in order to be able to use a mean field theory for this. So with this, we were able to find the distribution of water. So here you see on the top the adsorption and on the bottom the desorption as the relative humidity is increasing and later decreasing. And this is the example with water. And you can see that usually when people do adsorption and desorption of water in cement, they observe a hysteresis. And the reason for this hysteresis is this ink bottle cavitation effect that you are seeing in red. So basically, the material, it takes much more time to desorb the amount of water. So the next step in this simulation, it was that once we know the distribution of water around the grains, we want basically to get the poromechanical effect. We want to couple the fluid with the solid. And we did this by computing the capillary stress per particle. To do so, we had to do the Voronoi tessellation. This is this grid network that you see in this light blue color on top of the purple grain. So this is in order to distribute the water in a way that we get forces that are equal and opposite overall. So then we can use these forces to do molecular dynamics. So basically now, usually we were doing simulations with only pairwise interactions between the cement grains. This will keep the grains together. This is because of the nature of CS8. They're sticking together. But now we can add extra forces, the capillary force that each particle has due to the water distribution around it, and this will show us how the material is relaxing due to the distribution of water at different relative humidities. So now that I finished with explaining you the technique, we'll go through the results of this study. So the first interesting result is the adsorption and desorption of nitrogen and water in cement. So this again something that a lot of people have been trying to model to obtain the hysteresis, especially in the case of water, but I think nobody could have an agreement up to now. So as you see here on the figures, we have a very good agreement with experiments. Of course, in the case of nitrogen, the hysteresis is very small, but in the case of water, we're able to capture all these ink bottle effects that are giving rise to the hysteresis. So basically, as long as we have the right interactions from atomistic scale, and also we have the right grid size, that should be very small, because we need to have the fluid, which is water-based, so water molecule 3 angstrom, and we need to have a realistic pore networks for cement, so we need to go up to half a micron in order to have the full pore size distribution. Of course, the simulations were very heavy because of this reason, but they're doable due to parallelization. One more thing that we did is that once we have the distribution of water, as I told you, we can then relax the structure, so see how the solid matrix will change, and then repeat the adsorption. This is like when people on experiments, they do multiple cycles of adsorption desorption. You can see this, we did it for water. For nitrogen, there is no big difference, but for water, it's the two lines that are on dust. So basically, the hysteresis is reducing a little bit because we have a better packing of the cement grains. So the next point is that from adsorption desorption curves, we are able to determine the pore size distribution. So a lot of times in the literature, there are results of pore size distribution that are reported using water as a adsorbent. And this is basically, as you can see here, from the comparison between the simulations and the experiments, because we can probe the pore space in the simulations with a Monte Carlo technique. So basically, we take a sphere and we can really probe the geometric space, but we can also compute the pore size distribution from the isotherms, like they do in experiments, and compare the two and see which one is giving the best results. So clearly, the nitrogen is the right adsorbent in order to probe the pore space of cement, because it can capture the first peak of the gel pores and this broader distribution of pores. Water is giving a weird double peak in the beginning and also is not able to capture the long tail of capillary pores. So it does a very bad job on determining the pore space of water. So the next thing that we could do was to study the drying shrinkage in cement paste. So here, as I told you, is the part where we put back the capillary forces in the solid and we relax the structure with molecular dynamics. So we did this in two different ensembles. In the one ensemble, we keep the volume constant and we measure the pressure. And in the other ensemble, the NPT, we keep the pressure constant and we measure the shrinkage, the volume differences. So on the bottom figure, you can see the comparison that we have with experiments. So we are able to model the drying shrinkage of cement as a function of the relative humidity. And the experiments are in agreement for what we call the H paste. So once we have removed eigenstresses from the paste. But we did the same for a paste that had still eigenstresses, so it will be kind of fresh after the cement has been set. And in this case, this is the green and purple lines that you see there. You can see that we have a very interesting and non-monotonic behavior with the relative humidity. And what it shows us, the results of the simulations, is that if we cure cement with relative humidity between 30–40%, is where we get the least shrinkage, and at the same time the eigenstresses relaxes the best. So in a way, what people have always been doing, covering cement with a thin layer of water and the plastic to avoid evaporation, it's also confirmed by simulations that even at the nanoscale, this humidity is preventing the material for having extreme volume changes. Then with the simulations, we can of course go and understand where exactly we have the larger capillary forces in the material. So we have a resolution down to the cement nanograins, so down to few nanometers. And here we can basically color code each particle with a capillary force that is filling due to the water. So you don't see the water here, but you see from the color code, the bright particles are the ones that they have the larger capillary forces. Also, on the left, you see the distribution of capillary forces for different relative humidities. And The interesting thing is that at relative humidities that are low, we have this long tail of capillary forces, which are the highest capillary forces that are seen. And if you notice, the values they go up to 2.5 nanonewton, which it's good news because it's much smaller than the particle-particle interactions, the CSH-CSH interaction, which is around 10 nanonewtons. So we are safe. As we know, water is not destroying cement. Let's see where are localized this part of the tail. So let's see where are the highest capillary forces. So here is the same figure, the same snapshot you saw before, but now we only focus on the particles that are within this box, so on the tail of the distribution. And this green interface that you see on the snapshot is basically the interface between the solid and the pore. So basically all the particles that have high, strong capillary forces are the ones that are sitting on the surface of the solid between the pore and the solid, and especially the ones that are in junctions between small pores and larger capillary pores. So then, okay, we know that overall the magnitude of the forces is not strong enough to destroy cement, but let's see if these particles that they have high forces, can they have local events that they might be the precursor of cracks? To answer this question, we went further to understand the irreversible local deformations of this material, and to do so we use what is called nonaffine displacements. Here is a cartoon to explain what are nonaffine displacements. So basically here we have a shear deformation of a polymer, and the affine part, you see it in green, so basically we could reverse it back if we do the opposite deformation. But what we are interested in is the red particles, the non-affine part. So what part of the deformation is left that we cannot reverse back? So here you see exactly this type, the particles that they have the highest of this type of deformations colored in dark color. So in one case we have relative humidity 30%, and in the other 90%. And from these maps we see basically that there are a lot of these events, but at the moment they are not percolating. So they're not percolating in a way to form a crack. Of course, those were simulations that we were relaxing the structure with no extra load. And an interesting thing that we want to explore in the future is what is happening if we also have a load, because of course in real conditions on cement there is always some load. So this will be interesting to see if this type of isolated local events that we see here, if they will form a percolative path through the structure and will create a crack. So also here we can see the correlation of these events. The correlation of these events has a power law dependence, which has been observed also in glassy systems, but in our case, because cement has these pores, you can see that these events somehow they are arrested because of the pores. So their correlation length is coinciding with the length that we have found from scattering experiments, and this is due to the pores. So basically, in a way, the pores of cement are helping to arrest this type of irreversible deformations that they might have led to cracking. Also, this gave us a way to find a homogenization length. So the idea here is to find a length where probably we could average our results, and this could help us to upscale and go and model cement on larger scales. So for example, here you can see how the capillary pressure is distributed in our sample. Not anymore, you see that with the color code we we are able to go to regions that are 100 or 200 of nanometers, and we can forget about the grains that are only 5 nanometers. And what you've seen here is that, of course, on the lower relative humidities is where we have the highest capillary pressure, and this is mostly localized in the densest part of the solid, where we have a lot of small pores. Whereas the blue path that you see around, this is basically the large capillary pores that somehow there the capillary pressure can be released, so it's not so high. So this is the work that we've done to understand how water is distributed and what is the effect that has on the mechanical relaxation of the material. And now the next step is to introduce the ions. So now we want to understand, in case we have ions, is this gonna cause damage to cement? Because up to now, with water only on ambient conditions, we're doing good. So here, the idea, as I explained before, and I'm going to say again here now, is that we have ions confined between the new phase, the ice. So here I'm going to focus on the freeze-thaw damage, and the cement. So there is this nanometric layer that has a high concentration of ions due to confinement, and these ions are basically pushing both solids. And the important point is that, as we are seeing here on the phase diagram of water, is that we don't have freeze-thaw damage at 0 degrees Celsius. We have to go down to -5, -7, -8 to start observing this damage. This is because ice needs to develop a pressure high enough that can withstand this ionic pressure. Otherwise, as long as the ice is kind of soft or has a low pressure, is melting back due to the ionic pressure, and the cement is protected. Once the temperature is low enough and the ice has a higher pressure, then the ionic pressure is transmitted back to the cement. So to understand this type of phenomenon, we did a simulation on 2 steps. The first step is on small scales. So we go exactly in the interface between ice and cement. So here you see the simulation. We have an ice slab and a CS8 surface, and we use sodium ions, and we have these slabs on different distances, and we measure basically the pressure that it's created there. And of course, this pressure will depend on the different concentrations and on the different types of ions that we are using. So here the results are for sodium ions on different concentrations. And we can see that we have a repulsive pressure that basically the distance on which is shooting up is increasing as we increase the concentration of the ions. So once we had these pressures, we can turn this pressure into an interaction potential between grains of ice and grains of CS8s. So now we go to the next step of the simulation, where we're going to have the sample of cement that you saw before with the cement grains. The cement grains interact with the CS8's interaction as before, and now we will introduce ice grains that they will have an ice-ice interaction such that they can build a solid of ice that has the right mechanical properties of ice. And at the same time, we have an interaction between the 2 phases, the CS8s and the ice, that came from the smaller scale simulations. So we start with the cement configuration, and we are introducing the grains of ice with a grand canonical Monte Carlo simulation, and we are observing that first the ice is clustering in the pores of cement and eventually is percolating the structure. let's go and see a bit in detail what is happening there. So here I'm plotting how the porosity is changing and also how the box volume increases with the ice particle density. So we see that first the porosity is increasing inside the system, so that means that ice is helping CSH to pack better, but after a while the whole system starts to expand. So we start observing volume changes macroscopically. So we're going to look 3 points in detail to see what is happening. So the first point is where we have the increase of porosity, the second where we have the macroscopic increase, and the final state. So initially, when we have the porosity increase, if we decouple the two networks, so if we plot the cement on the bottom and the ice on the top separately, we see that we have formation of ice, but it's all stays inside the pore. So we have clusters of ice inside the pore. Where we start observing the macroscopic volume changes is when we have the percolation. Once the ice is percolating through the network of cement, it has basically a collective effect that is pushing the whole solid of cement, and that's why we're observing a macroscopic volume change. And of course, finally, we have the formation of really large cracks. The interesting thing here is that from the phase diagram of water, we can go and find the temperature that corresponds to the pressure that we computed on the small scales between the interface of cement and ice, and plot it as a function of the sodium concentration that we have. And here we see that we are having a good comparison with experimental results that are shown in red and black. So that gives us an idea that we are doing, we have a good estimate for the pressure where the material is freezing. And now I'm going to move to the last part of this talk, which is about mitigation strategies for these durability issues that we discussed. Again, I'm going to focus mostly on freeze thaw, but a lot of the ideas are applying also to alkali-silica reaction problems. So the usual technique to prevent freeze thaw is air entrainment agents. So in this way, small bubbles are introduced in the concrete, and what they really do, you can see here on this tomography picture, is they create space inside the cement where ice can grow, and also this ionic pressure can be released. So basically, in a way, they are postponing the saturation point, and like this, the damage is taking longer to occur. A different strategy is to make cement hydrophobic. So basically, as we discuss all this time, what is the big problem of cement is water. As a material that it's porous on different scales, and it's always connected to the outside. So basically, water as a solvent can dissolve ions that they can always they can penetrate the material to all different scales. So if we're able to make cement hydrophobic and prevent the solvent from going inside, we could prevent a lot of these durability issues. So some techniques to make cement hydrophobic include to use silanols. This is usually for surface treatments, and it's usually an expensive technique. So the technique that we're suggesting here with some colleagues like Roland Pellenc, Franz Ulm, Thibaut Divou, which are all people from the hub, but also Nicolas Anou, Renal Bakov, which are people working at MIT and at CNRS, is to use cement carbon composites. So this is a patent that we have recently between CNRS and MIT, And you can find it online. It describes how one can make this type of composite and all the properties of this material. So I'm going to explain to you very briefly how we make this material and what we can gain for durability issues. So the idea is very simple. Basically, we're mixing cement with nanocarbon particles, which are, there are two materials that are both very cheap. So overall, you have a black cement, which is very affordable, and this material has several properties that they all come from the fact that we have a percolative network of carbon nanograins inside the cement. So the first thing is that the cement paste becomes conductive. So the carbon is a conductive phase, and as long as it percolates the material, we have a conductive cement paste. So this material, we subjected it into freeze-thaw cycles. So on the left, you see the normal OPC cement with no carbon nanoparticles, and on the right, the one with carbon nanoparticles. And you can see that we can prevent freeze-thaw damage using the carbon nanoparticles. The reason we can do this is because carbon is, on one hand, is hydrophobic. So we have a smaller amount of water in the material. The second thing is that these carbons are all porous carbons, so they have pores where the ions can be stored. So basically, that's a way to reduce the ionic pressure, because these ions, they don't have to go and sit in the nanometric layer between water and ice, but they can go and sit inside the carbon. And on top of this, this material has the so-called Joule effect. So as long as we plug it in on a small voltage, we can increase the material of the temperature of the material. Here you see by 5 degrees, but on recent results, we can go even to 100 degrees. So basically, the same material, it's preventing freeze-thaw at the same time, by its own, but also if we plug a small voltage, we can basically melt the ice and even evaporate the water. So we have a synergetic effect of the two that can prevent completely the damage of freeze-thaw. And another interesting property that has this material is that it can store energy. So here you can see the results for the capacitor effect. So basically, by mixing the two and using an electrolyte and a separator, we can build a capacitor that can store energy and change totally the view that we have of how we can build and design infrastructure. So with this, I would like to thank you for your attention, and I'll be glad to take any questions.
Great. Thanks so much, Katerina. As I mentioned to everyone, we welcome your questions. Please type them in the Q&A box that's in the lower right hand, and then I can pass them on to Katerina. And while we wait for some questions to come in, maybe I can get started with a couple. It's interesting talking about this cement nanocarbon as an opportunity to mitigate freeze-thaw damage. What do you think? What kind of impact do you think this would have on traditional strategies of air entrainment? Do you think that it's something that could be coupled with air entrainment, or would maybe even replace it? I know it's kind of early days in that, but I wonder if you have a sense of that.
Yes, I think the idea here is, for example, on what I showed you before, the one that's also in the screen now, we don't have any air entrained, and we totally avoid freeze-thaw. So basically, the idea is that once you mix in the nanoparticles of carbon, you don't need another agent. Mm-hmm. Mm-hmm. Of course, I suppose the two things can be coupled and work together. But for the moment, we didn't need to add air entrainment.
Great.
But I think there is a plan with the people in the lab to see how the two are working together.
Great.
Yep.
Great. All right. We do have a couple of questions coming in. One of them, I'd like to ask you about the software used in the simulation for building the pore structure, and also which technique have been used to scan specimens. So maybe two of them. The software used in the simulation for building the pore structure. Let's start with that one.
Okay, so we don't use a specific software in the simulation, so we are using an open source code, LAMPS, for molecular dynamics, but
and that's just to be clear, that's LAMPS, is that right?
LAMMPS, yes.
Double
M, yes.
Thank you, yeah, okay, yep.
So, so this is an open source code for molecular dynamics, but for example, the DFT code, it was a homegrown code that took a long time to be developed because it had to be parallelized to handle the very small grid that we had to use. So part of the code is homegrown. Then we use LAMPS for molecular dynamics, and most of the analysis, again, we do with our own codes. So there is no really software out there that can do everything at one time. And the second was how
the technique used to scan specimens.
You mean like for tomography here? It's all done with our collaborators in Marseille. In terms of characterizing pore size distributions, again, on the simulations, we have codes that they can do it geometrically, like a Monte Carlo code where it's probing the pore space. And also from the adsorption and desorption techniques, we use experiments from the literature. They're all published in the publications I've put out there. I don't know if this covers, I'm not sure what was the exact question about scanning the specimens.
Yeah, sure.
If the person wants to give us more clues.
Sure, yeah. All right, the next one is, how do you think the incorporation of soluble polymers such as polycarboxylate-based superplasticizers may modify these pressure distributions?
So this is in the making of the cement paste without carbon black. So just the addition of a polymer, I think I don't think so it will have a significant effect. Maybe because the polymer will absorb water, it might shift a little bit. It might postpone any type of damage with the idea that it's an absorbent polymer. Then the idea of using superplasticizers or any type of admixtures can be useful for incorporating a larger amount of carbon in the composite. In principle, the additives should not have an effect on the lifetime of the paste.
But do you think they would actually be beneficial or have limited impact?
I think that they are very beneficial at the initial stages. So basically, for keeping the viscosity of the paste of the cement longer fluid, but once the material is set, I don't think so that they have a big impact. And also, usually they are added on such a small percentage that is not a big part of the cement paste.
Okay, great.
Yeah.
All right. Another question is, did the upscaling process take into consideration hydrate size, morphology, and distribution?
We have polydispersed size on the cement hydrate, so we do take into account the different size of the hydrates, but at this stage we don't take into account the different morphology or roughnesses on the surface of the aggregates. That's a very interesting question, and we are trying to work on this with colleagues in Montpellier. applying more granular techniques. So I hope we'll have more results on that front soon.
Great. There's another question about whether or not the presentation is available, and the recording will be posted to YouTube. Katerina, if you don't mind, if they send an email to cshub@mit.edu, can we share a version of the slides? Is that okay?
Yes, definitely.
Okay.
Definitely.
So yeah, just send an email to cshub@mit.edu, and we'll get you the slides. I maybe had another question about, you obviously focused on mitigation strategies for freeze thaw, but you know, as you talked about, there's a lot of commonality in the mechanism that's occurring for both freeze thaw and ASR because of what's occurring at the interfaces. Do you see similar opportunities to use then some of what you've learned to also mitigate impacts of ASR?
Yes, exactly. So we think that, for example, the carbon nanoparticles can help also a lot with alkali-silica reaction, for the reason that the porous carbon has pores where the alkalis can go and stay there. So instead of forming a gel phase in the larger pores, they just stay inside the carbon black. So that would be an idea that will help mitigating this. Of course, the problem with alkali-silica reaction experiments, as we all know from the hub, they take really long.
They do, exactly.
We need to expose the material in such conditions for a very long time to observe this. So freeze thaw was an easier thing to show.
Yeah. Okay, great. All right, a couple other questions. How would the presence of filler inert particles in different sizes modify these results, such as limestone or fly ash?
Yes. So at the moment, the carbon nanoparticles, they are also, in a way, they're a filler on the material. They're filling up the pores, so the less porosity, the less water can go in. So probably also different type of fillers have such an effect, but it depends if they are hydrophilic or hydrophobic, these fillers. And more specifically, we are on the process to upscale this material, so we are building, we are making a mortar out of it. So there we will investigate all these different type of fillers.
Great. Okay. There's a question about the picture that you have up here right now with the carbon nanoparticles figure on the right in particular. The question is basically, it appears to show cracking of the paste. So first, is that true? And then the follow-up question is, was air entrainment used in the paste without carbon nanoparticles? The one on the left then.
Yes, no, both materials were mixed in the same way, so there was no air entrainment in none of them.
Either one.
So and all of them, they were saturated with water, 100%. So in one case on the left, we see clearly macroscopic cracks that they have percolate the sample. In the other case, maybe there are nano cracks, but they have not percolated the sample yet. So of course, it's very interesting to find on after how many cycles we will observe damage in the case with the carbon nanoparticles. But on the same conditions, we definitely, in one case, we have a fully cracked paste, and with the carbon nanoparticles, we don't observe macroscopic cracks.
All right. Well, I think that's all the questions that we've had. Thanks, Katerina. The kind of all the questions that we got shows us there's a lot of interest in this. And as I mentioned, you can go to our YouTube page. This will be posted there in the next day or two, and you'll also get a notification via email when those are posted. And then if you did want the slides, just send an email to cshub@mit.edu, and we can get them to you. And we look forward to having you join us again next month on the next public webinar. Thanks so much, everyone, and thanks to Katerina.
Thank you, too. Have a good day.
Bye-bye.